questions from our homework that we want to go over. Some of them can be a little bit tricky with the truth statements. Luke?
66.
66. All right, so 66 has said, which statement has a true converse? So remember, the converse switches the hypothesis and the conclusion. So the mistake a lot of students make is that they just read the given statements and identify which one is true. So you have to think about the converse. So if a vehicle has 4 wheels, then it is a car. That would be false because it could also be a truck or a van. So that's why the converse of it was false. So that was not my answer. If you cross an ocean, then you go to Asia from the United States. That's also false. You could be going to Europe or Spain. You don't have to be going to Asia. If your pet is furry, then you own a dog. Could be a cat. So that one was false. If you can walk, then you can stand up. Well, walking, you're standing. So that was why that one was. Again, make sure that you were looking at the converse, which again switches the hypothesis and the conclusion. So you had to actually think of the converse of each one before you identified true or false. Next one. Marquise?
43.
All right, so 43, the directions that said write the converse of each statement. If the converse is true, write true. If not, provide a counterexample. So the original statement had said, if x equals -6, then the absolute value of x equals 6. And that's saying if we were to plug this in, the absolute value of -6 is +6. So the original statement, they didn't ask us this, but the original statement was true. The converse is to change the hypothesis and the conclusion. So if the absolute value of x equals 6, what it's telling us that then x must equal only -6. This is false. X also could equal a +6 because the absolute value of +6 would also be 6. So again, you always want to leave the hypothesis part as is. You can't change it. What you're asking yourself is, does it have to be only this answer? Could it be another answer? If it can be, then you'll say false and then state that counterexample. It does get confusing for some students, like when they switch around, but the big thing to remember is that you are keeping the hypothesis part as is. So for example, in this one, it says x equals 2. We're not saying x could equal -2. We're stating x can only equal 2 is my hypothesis. So if I take 2 and I plug it in, 2 squared does equal 4. So the original statement was true. Now when you flip it around, if x squared equals 4, then x must be 2. That was false because, again, if you solve this for x, you will get a positive and a -2. So it could be one or the other. But good question. A lot of students struggle with which one is the true one, which one's not. So just leave that hypothesis. Next one. Some of you didn't read the directions on the back and I think you thought the sentence in your head, you just didn't write it out. So just make sure you would write the words. Remember, the arrow symbol is the conditional symbol. So really, you're always going to put the word if before whatever statement P is. The arrow goes where the then would be in the sentence. So that's why we got if a figure is a square, then, you could also say then that figure has 4 congruent angles. I just said then it has 4 congruent angles. And they asked us to provide a truth value, and you can see these. Again, I would probably choose ones that were using things we know a little bit more about. You should know about quadrilaterals, but until we go over the relationship between all of them, that a square is actually a rectangle also, but a rectangle is only sometimes a square based on the properties. But we'll talk about all that when we get to our quadrilateral unit. We'll talk about parallelograms, rhombus, trapezoid, all that stuff. Any other ones you want to go over? Any perfects? No perfects. Miss between 1 and 3. Okay. we go over the ones we wanted to? Okay. All right, then to make the lesson a little bit less boring, go ahead and move around the room and get with a friend of your choice. You guys can push your desks together. I'm going to be doing an example, then I'm going to have you guys do one together. We'll go over it, same thing, just so I'm not just reading to you at the board. Pass up the answer keys. Thank you, Brett. So yesterday we looked at the conditional, which was an if-then. Today we're looking at what's called a biconditional. Okay, so similar, but it actually can be written both ways. In contrast, where yesterday if we wrote the converse, sometimes it was false and the conditional was true. So this is going to be when you combine a conditional statement and its converse together. You will create a biconditional statement. The biconditional statement is in the form if and only if. So it's a statement that can be written in the form P if and only if Q. So conditional is if then, a biconditional is if and only if. And again, it's going to be telling you that the conditional and its converse are both true. There's also an abbreviation for this, so if you didn't want to have to write out if and only if every time, you can write IFF, which stands for if and only if. Why, I don't know, but that's the abbreviation you can use if you like. And in your homework in class today, like instead of writing out the word perpendicular, like you'll see me use the symbol. Same with parallel, just to shorten your writing. So I know there's a lot of writing with this unit. So again, what this is really telling you is that technically the biconditional is if P, then Q, and if Q, then P. Okay, because this would be the converse. So it's really saying that you have both together, but without having to write two. Okay, the notation is a two-way arrow. So P double arrow Q. And again, that really means that you can have if P then Q and if Q then P. Converse and conditional. All right, so the first set of examples ask us to write the converse, then write the biconditional. We don't have to state any truth values here. So remember, what does the converse do? From yesterday, what does the converse do? Right?
It flips the if and
Good. It flips your hypothesis and your conclusion. So our converse would be if x equals 9, then 5x minus 8 equals 37. Now they don't ask us to find the truth values, but we actually probably should, because the only way you can write a biconditional is if they're both true. Okay, so if you look at it, if we were to solve this and add 8, we would get 45, divide by 5, we would get 9. So this one was true. And the converse, if you were to take 9 and plug it in, 5 times 9, 45 minus 8, 47. So this would be true. So since they are both true, we can write a biconditional. The biconditional, again, takes out the if-then. It doesn't matter which one you put first. Like if you put the 5x minus 8 first and x equals 9, or the other way. Since there's a two-way arrow, it doesn't matter which one you put where. In between them, you will write the phrase if and only if. So 5x minus 8 equals 37, if and only if, or if you want to abbreviate it, IFF, x equals 9. Again, you also could write it as x equals 9, if and only if 5x minus 8 equals 37. It doesn't matter the order this time, because it's two-way arrow. All right, work with your partner to come up with the converse and biconditional for the next one, and also identify truth values with those. All right, so that's what we should have. If two angles are congruent, then they have the same measure. Again, for abbreviation purposes, if you guys want to put an angle symbol and you want to put a congruent symbol, just so you have to write less words, that's fine. Okay. And who can tell me what they got for the biconditional then? Biconditional? No?
Two angles are congruent if and only if they have the same measure.
Good. Two angles have this. Oh, I put it the other way. It doesn't matter though. Two angles are congruent if and only if they have the same measure, or two angles have the same measure if and only if they are congruent. Okay? All right. The next set of examples are written as biconditionals. The directions ask us to separate the biconditional into a conditional and the converse. So as you see, there's an if and only if in the middle. So if we want to write it as a conditional, that's your if, then. So all you're going to do is take the word if, put it in the front, get rid of the only if, and change that to a then. So we would say if an angle is obtuse, then its measure is greater than 90 and less than 180. Again, to shorten your workload, you could put a greater than, a less than symbol. Feel free to abbreviate wherever necessary. Now, technically, since a biconditional, you can switch it around. You could have said the converse first. It doesn't really matter. But whenever you write whatever you choose as your conditional, you will then flip it for the converse. So we're going to change around our hypothesis and conclusion, which would be if an angle is greater than 90 and less than 180, should have degrees there, then it is obtuse. Do you think we need to do the next one, or do you get it?
Yeah.
I get it.
Okay. I'll show in case anyone's watching my video. We all know. No one is, but nevertheless. So this is just a box that reminds you of what the symbols tell you. Now on the back, we're going to be recognizing good definitions. So in geometry, we're going to do a lot with definitions. You've seen vocab on every quiz you've taken. And that's because in Chapter 2, we're going to start doing our two-column proofs. And sometimes our reason will be the definition of a midpoint or the definition of perpendicular lines. So in geometry, biconditional statements are used to write good definitions of words. So in order to write a good definition, you have to prove that your if P then Q and if Q then P are both true, it can be a definition. So a definition is defined as a statement that describes a mathematical object and can be written as a biconditional, which again, biconditionals are if and only if. Well, so some of the questions you'll see in your homework will say, is this a good definition or not? The easiest way to test if something is a good definition is to write it as a conditional, write the converse, and make sure that they're both true, that you can read it both directions. Now, a good definition should be help you to identify or classify an object. A good definition also should use clearly understood terms, or commonly understood. It needs to be precise. So for example, you can't just say a square is a shape with four sides. Like that would be a bad definition. It's not precise. Okay. Also, if I were to say, if something is a square, then it has four sides. That's true. If something has four sides, then it's a square. That's not true. So that's why it would also be a bad definition. You have to test both ways.
Is that some can or
Sorry? Can be written. And then again, as I just explained, the good definition has to be reversible. You have to be able to write it as a converse and the regular conditional. One way to show something is not a good definition is the same thing we did yesterday, which is our counterexample. So for example, when I said, if something has four sides, then it is a square, the counterexample could be what? If something is a rectangle, a parallelogram, a rhombus, anything with four sides would prove that wrong. All right. So we'll probably only do one of these because I think you guys are doing okay. And let's do B because it's shorter writing-wise. Okay? Okay. All right, so it says, show that the definition is reversible, then write it as a true biconditional. So it says a right angle is an angle whose measure is 90 degrees. That is the definition of a right angle. So who could write that as a conditional statement for me? A conditional is our if, then. Who can write that as a conditional statement? We did this yesterday. Maddie?
If an angle measures 90 degrees and it's a right angle.
Yeah, you could say that. I have it the other way probably first. I probably have if an angle is a right angle, then it measures 90 degrees. But you could do that first. Your converse will then be the one I just said. But just for what I have, I know is behind this box. If an angle is a right angle, then its measure is 90 degrees. But she said, if an angle measures 90 degrees, then it is a right angle. That would be the correct thing, too. Yours would just be flip-flopped here. Then our converse, we'll flip it around. Like Maddie said, if an angle measures 90 degrees, then it is a right angle. We can verify that both of these are true, right? And then who could write this as a biconditional for us? A biconditional. Marquise? Wait, remember, what form is biconditional in? Both. But what's the phrase we put in the middle? If and only if. So, Brett?
An angle measures 90 degrees if and only if it is a right angle.
Good. An angle measures 90 degrees if and only if it is a right angle. Or, an angle is a right angle if and only if it measures 90 degrees. Doesn't matter which order you choose. Okay, I'm going to put this up just in case anyone wants to watch this. And I'm sure I'll get 0 views.
That's the same thing with Mr. Foley's videos. He always asks and nobody raises their hands.
Well, we can see how many views, so it's not good to lie. Someone on period 12 honors algebra 2 told me they watched all the videos when they were absent. I had 0 views. Did you? Good.
I didn't watch the video.
Well, you should only watch the video if you're absent or you're struggling. We have no one absent today, so no one in this class should be watching it. But in every class, I have usually at least one person absent. All right. The last set of examples ask us to state if it's a good definition or not. So again, in order for it to be a good definition, it has to be able to be written as a biconditional. You don't have to write it out, you can just think it in your mind. So, if a figure is a square, then it has 4 right angles. If a figure is a square, then it has 4 right angles. Is that true? If a figure is a square, then yes. Flip it around. If a figure has 4 right angles, then it is a square. Yeah.
False.
False. What's our counterexample? A rectangle. Okay, so this is not a good definition. It's not reversible. And that's probably what I wrote. So I have no, a rectangle also has 4 right angles. The reason that it's not a good definition is that it's not precise and it's not reversible. And if you pick no, that's usually always your explanation. Is that it's not precise and not reversible. And then the next one's almost comical. Do we think that's a good definition? This one would not be precise. It also has nothing to do with the fact that it has 3 sides, which is a triangle, but it's also not reversible. And then go ahead and try the closure down there while I pass out the homework. You guys have some time to start on this in class. Okay. Well, we do have a quiz on this material on Tuesday of next week. It should be a really easy quiz. You should have a lot of A's on it. to,
How many points is it? I like this stuff, because I like it.
well, we'll get into groups and we'll love it. So for the closure, we should have, the converse would be if x plus 15 equals 20, then x equals 5. And the biconditional would be x plus 15 equals 20, if and only if x equals 5. And of course, they are both true, so that's why we were able to write them. Now on the homework, let's suppose that this was false, okay? You would not be able to write a biconditional. So in some of the homework questions, it will say, write the converse. If both are true, write a biconditional. So if one of them is false, you don't write a biconditional, okay? You guys have the rest of class to go ahead and work on that.